So in this video, we will discuss diesel cycle. So we will try to derive variables or equations that is necessary in solving the different states or different points of the entire cycle. Okay, so the first thing that we need to do is for us to identify first the process from each point. Okay, so let's start first with point 1. So my tip is for you to locate first the straight line. So this is the PV and the TS diagram of an ideal diesel cycle. So in order for us to determine the process, so let's locate for straight line. So in this example, the PV diagram from point 1 to 2 is not a straight line. So but in your TS curve, it is represented by a straight horizontal line which is given by S or constant entropy. So that is an isentropic process from 1 to 2. Next, from 2 to 3, we have a constant pressure process, so that is P is equal to C. From 3 to 4, this is not a straight line, but here in the TS curve, it is represented by constant entropy, so therefore that is isentropic relation. So at 4 to 1, it is represented by a straight vertical line, which is represented by V or isochoric process. Okay? So it is very important for us to determine first the process that the cycle undergoes before deriving the equations. Okay? So in the previous video, in an Otto cycle, we are already introduced to RK, which is the compression ratio V1 over V2. Okay, so in diesel cycle, there are several variables that we need to introduce to you. So we have the cutoff ratio. Cutoff ratio is basically the ratio V3 over V2. Okay, so the volume at point 3 relative to volume number 2. Next, so let's write that RC. Okay, next. The next one is the expansion ratio. So expansion ratio is basically the power stroke of the cycle. That is V4 over V3. Okay? So as you can see here, if we multiply RC multiplied by RE, so RC is V3 over V2 times RE, which is V4 over V3. So as you can see, V3 here will cancel out, leaving us with V4 over V2. But as you observe in the PV diagram, V4 is equal to V1. So we can replace V4 here with V1. So we have V1 over V2. So as you can see, V1 over V2, we simply arrive with our compression ratio, leaving us with the conclusion that aside from V1 over V2, RK can also be solved by using RC times RE. Okay, so your cutoff ratio multiplied by your expansion ratio. Okay, so let's start. So let's start first with heat addition. So where does heat addition takes place? So in an ideal diesel engine, heat addition takes place in points 2 to 3. So that is your heat addition. Next, in points 4 to 1, this is where your heat rejection takes place. Okay? So just like in Otto cycle, so 2 to 3 is heat addition and 4 to 1 is heat rejection or your exhaust stroke. Okay? So let's start first with the efficiency of an ideal diesel cycle, which is E. So for all gas cycles, it is given by work net over QA. Okay? That is for all gas cycles. So let's try to derive the efficiency for specifically for diesel cycle. Okay? So let's start first with the work net. So that is letter A. Okay? So for the work net, it is given by So for all gas cycles as well, QA plus minus the absolute value of QR. Okay? So we need to solve first for QA. So in QA, we've said that it occurs from point 2 to 3. However, let's determine first what type of process is 2 to 3. Okay? So we've said earlier that this one is a constant pressure process. So therefore, QA is CP or specific heat during constant pressure quantity T3 minus T2. Okay? So this one is equation for heat addition. Next, what about the equation for heat rejection? That is letter C. Heat rejection is given by, so heat rejection takes place in 4 to 1. So that is MC. So what type of process is that? So the type of process is constant volume. So therefore, CV quantity. So the final point is T1 and the initial is T4. So T1 minus T4. Okay? So in this case, we can interchange this one for it to be upper limit minus lower limit. So if we interchange that, so this left side must also interchange their sign. So MCV here will become negative MCV T4 minus T1. So it basically utilize a negative value in front for it to be balanced. Okay? So by substituting B to C, B and C to equation A, so we can solve for the work net. That is work net is equal to QA. So QA is given by MCP T3 minus T2 minus MCV T4 minus T1. Okay? So since we have the work net already and we have QA, we can solve for the efficiency. Okay? So efficiency is equal to work net. So let's write it down. So MCP T3 minus T2 minus MCV T4 minus T1 over, so QA is MCP T3 minus T2. Okay? So as you can see, in the numerator, we have two separate terms sharing the same denominator. So we can split them up. Okay? So what we will do is we'll have, so let's split first the numerator. So we have MCP T3 minus T2 over, so copy the denominator since they are sharing the same denominator, T3 minus T2 minus, so this one is a minus, MCV T4 minus T1 over MCP T3 minus T2. Okay? So as you can see, the first term, this one, they are equal to each other, therefore they will be 1. And the mass here, we can cancel out in the second term. And as you observe here, this one is CV over CP. So in our specific heat ratio, we have CP over CV. So therefore, this entire term, we can rewrite it as 1 over K. So we have the efficiency is equal to 1 minus T4 minus T1 over K quantity T3 minus T sub 2. Okay? So as you can notice, all of our equations are dependent on temperature. So we need to solve for T4, T3, and T2 because T1, most of the time it is given or you can derive it from equation of state. Okay? So let's write this down as equation D. Okay? This one is equation D. So let's try first to solve for t sub 2. Okay? So since we are at point 1 already, so we want to go to point 2. Okay? So point 2. So from point 1 to point 2, the process that we went through or we undergo through is an isentropic process. So therefore, we need to solve for t sub 2 isentropically. Okay? So how are we going to do that? So we will use isentropic relation. So that is T2 over T1 is equal to V1 over V2 raised to K minus 1. So as we've mentioned earlier, V1 over V2 is your compression ratio. So we can rewrite this one. So let's isolate T sub 2. So T sub 2 is equal to T sub 1 quantity Rk raised to K minus 1. So this is your T sub 2. So let's put an underline here. So this is T sub 2. Next, let's try to solve for P2. Okay? So P2, so since that is an isentropic relations as well, so it will be V1 over V2 raised to K. So isolating P sub 2, we have P2 is equal to P1 quantity V1 over V2, that is Rk, raised to K. Okay? So next, so what about volume 2? Volume 2, we can solve that using our compression ratio. Okay? Next, letter F. Let's now try to solve for T3. Okay? So we're done here. So we are at point 2. We want to solve for point 3. As you can see, the relationship of point 2 and point 3 is isobaric process. So we can use the combined gas law. That is P2 V2 over T2 is equal to P3 V3 T3. So since the pressure is constant, as we've said in the PV diagram, so we can cancel pressure. Okay? So by performing separation of variables, so here I can cross multiply T3 and V sub 2. I will have T3 over T2 is equal to V3 over V2. Okay? So as we've said before, V3 over V2 is your cutoff ratio. Okay? So by isolating T sub 3, we have T3 is equal to T2 quantity RC, or your cutoff ratio. Okay? So we can expand this further because we've already solved for T2, and T2 is written by T1 Rk raised to K minus 1. So let's substitute that. So we will have T3 is equal to T1 quantity Rk raised to K minus 1 times Rc. Okay? So this is for T3. Okay? Temperature 3. So for V3, we can solve for V3 using the cutoff ratio. So once we've obtained the necessary values, we can already solve for V3. Okay? Next, letter G. So for letter G, let's try to solve for T sub 4. Okay? So once we're done with point 3, we want to go to point 4 down here. Okay? So the process that we've passed through is an isentropic process. So we need to relate T4 and T3 isentropically. That is T4 over T3 is equal to V3 over V4 raised to K minus 1. Okay? So as we've said that V4 from your PV diagram, V4 is equal to V1. So let's write it here. V4 is equal to V1, and V3 we've said as well. So we can solve that using the cutoff ratio, that is V3 over V2. So if we solve for V3 here, just cross multiply. So we have V3 is equal to RC times V sub 2. Okay? So if we substitute the necessary values in our equation, we will have T4 is equal to T3 quantity V3 is RC times V2 divided by V4 is equal to V1, so that is V1 raised to K minus 1. Okay? So as you can see here, V2 over V1, so that is simply the inverse of our compression ratio, because compression ratio is V1 over V2. So we can rewrite this as T4 is equal to T3 quantity RC over RK raised to K minus 1. Okay? So we can expand this one further. T3, we've said that this one is T3. So T4 is equal to T3, substitute this one. We have T1 RK raised to K minus 1 times RC. Quantity, so this term, RC over RK raised to K minus 1. Okay? So we can expand this one by distributing the exponent by loss of exponent. Okay? So we will have T4 is equal to T1 RK raised to K minus 1 times RC. Quantity RC raised to K minus 1 over RK raised to K minus 1. Just distribute the exponent from this term. Okay? So as you can see, RK raised to K minus 1 will cancel out, leaving us with T4 is equal to T1 times RC times RC raised to K minus 1. Okay? But as you can see here, we can split this up. So by loss of exponent, so if we have the same base multiplied by the same base, okay? So let's say we have x squared times x cubed. So the first thing that we need to do is for us to copy the base and then add the exponent. So simply this one is x raised to 5. So we can do that here. So we can write RC raised to K times RC raised to negative 1. So just copy the base. So since they have the same base, it will be RC raised to K plus negative 1, or simply RC raised to K minus 1. So we can rewrite it as this one. Okay? So what will happen if we do that? So it will be T4 is equals to T1 times RC times RC raised to K times RC raised to negative 1. So this RC right here has an invisible 1. Okay? So if we multiply these two terms, RC times 1, RC raised to 1 and RC raised to negative 1, eventually they will cancel each other out, because negative 1 plus 1, that is 0. Anything that is raised to 0, if we have x raised to 0, that will be equal to 1. Okay? So therefore, we have T4 is equal to T1 times RC raised to K. So that is the simplified version of your T4. Okay? So now, we've already solved for T4, T2, T3. So let's go back to our general equation. So we have the efficiency is equal to 1 minus T4 minus T1 over K quantity T3 minus T2. So let's double check. T4 minus T1, K, T3, T2. Okay? So let's try to substitute one by one. So T4 first. Okay? So we have the efficiency is 1 minus T4, that is T1 times RC raised to K minus T sub 1 over K quantity T3, that is T1 RK raised to K minus 1, T1 RK raised to K minus 1 times RC minus T sub 2, that is T1 RK raised to K minus 1, that is T1 RK raised to K minus 1. Okay, so we can simplify this one by one. So let's start first with the numerator. Okay, so efficiency is 1 minus, in the numerator we have a common factor of T sub 1. So let's factor out T sub 1. We have T1, so that is quantity RC raised to K minus 1. Okay, over, so in the denominator we have a common factor of T1 RK raised to K minus 1, right? So we can factor that out. We will have let's write first K. So K quantity, so we have T1 RK raised to K minus 1. So leaving us, so here if we factor that out, leaving us with RC only. RC minus this one, this entire term is factored out, so that is 1. Okay, so as you can see here, T1 will be eliminated. So we will have the efficiency is 1 minus RC raised to K minus 1 over K quantity RK raised to K minus 1 quantity RC minus 1. Okay, as you can see, we have 3 terms in the denominator, so we can split them up. So specifically, I want to split up RK raised to K minus 1. Why? Because as you can see here, if I do that, E is equal to 1 minus 1 over RK raised to K minus 1 times. So instead of using dot, let's use brackets. Okay, RC raised to K minus 1 over K quantity RC minus 1. So if I distribute this in this term, we will eventually end up with this term. So why did I separate RK raised to K minus 1? Because as you can see, in order for you to remember this one is the simplified version of your Otto cycle efficiency. Okay, so you can easily remember. However, in solving this one, you cannot solve this one first and then multiply it by this one. You cannot do that. Okay, because let's observe PEMDAS in our solving for the efficiency of a diesel cycle. So basically, this is the simplified version of your efficiency. So we have 1 minus 1 over RK raised to K minus 1 quantity. So RC, that is your cutoff ratio, so we have this one. So K is your specific heat ratio. So basically, if you are given in the problem RK and RC, you can immediately solve for the efficiency of your diesel cycle. Okay, so in the next video, let's try to utilize these equations by solving an entire cycle relating to diesel cycle. Okay, so I hope I can see you in the next video, and stay safe and have a nice day to everyone.